Assalamualaikum YouTube viewers. The topic of today's video is solid state nuclear track detectors. So in this video I'm going to tell you what is a solid state nuclear detector and how does it work. And secondly, I will give an example of CR39 as a nuclear track detector. Okay, so moving on. In this video, I'm going to cover all of this topic, the basic, the principle, the application, advantages and disadvantages, and an experiment also. Okay, so first of all, what we have here is what is a solid state nuclear track detector. So a solid state nuclear track detector, or SSNTD, okay, is also known as an etched track detector. So another name for the solid state nuclear track detector is the etched track detector or a dielectric track detector. Okay, so these are some other names for SSNTDs, and it is a sample. So what is a solid state nuclear track detector? The solid state nuclear track detector is actually a solid material. It is actually a sample of a solid material. As you can see here that it contains a word of solid state. Okay, so it means that it must have some solid material. So let's just say if that solid material is here, okay, if this is the solid material, so it is a sample of solid material of photographic film emulsion, crystal, glass or plastic. So this material can be a photographic emulsion, this can be a crystal, this can be a glass or a plastic. Okay, so if this material is exposed to some radiation, okay, so if this material is exposed to some radiation, some nuclear radiation like neutron or charged particle like alpha particle or a beta particle, occasionally also gamma rays. Okay, so what happens is when this ray falls on this material, okay, it will leave some path on the surface of the material. Okay, and these paths are so light that even they are not visible, even with the light microscope. Okay, so what we do is then to etch these paths. Okay, what we do is to perform the process of etching on these paths left by the radiation. Okay, let me repeat it again, that these radiations make some path on the surface of the material. Okay, and these paths are so light that even a light microscope cannot see these paths. So what we do is just to perform the process of etching on this material so that this path become visible, so that these paths become deep and visible through the microscope. Okay, so the next thing is that the tracks of the nuclear particles are etched faster than the bulk material, and the size and the shape of these tracks, okay, the size and the shape of the tracks that are formed on the surface of the material due to the incoming particle depends upon the mass, depends upon the charge, energy and direction of the motion of the incoming particle. Okay, let me repeat it again, that the size and the shape of the track that is formed on the surface of this sample, that is formed on the surface of this material, depends upon the mass, upon the charge, upon the energy and the direction of the motion of the incoming particle that is going to form the track on its surface. Okay, so the next thing is if particle enter the surface at normal incidence, normal mean if it enters at a 90 degree, okay, the pits are circular. The pits mean the tracks are circular, otherwise they form an elliptic track. Okay, if the particles are not formed, if the incoming ray is not at 90 degree, okay, if the incoming ray is not at 90 degree means if the incoming ray is at an angle like this, then the path that will be formed by these incoming rays will be elliptical. Okay, and if it is in the normal direction, if it is in the 90 degree direction, then the path that will be formed will be circular, and if it is in some other direction other than the 90 degree, then the path will be the ellipticity, then the path will follow the ellipticity, means that the path will be elliptical. Okay, so the next thing is, here is an example. Okay, as you can see here that this is the surface. Okay, this is the surface of a material, and as you can see here, this is the track that is formed by our radiation inside the material. Okay, and again this is another track that is formed by the radiation inside the material. Okay, so what happens is when the radiation has fallen on this surface, okay, when the radiation has fallen on this surface, okay, it has gone into the surface and formed tracks in the surface, in the solid. Okay, when another radiation has fallen on this surface, it has again gone into the surface and has made tracks inside the solid. Okay, so the next thing what we have here is the irradiation. Okay, charged particles which penetrate a solid can lose their energy via various interaction types. Okay, when the ray falls on this solid material, the ray will lose its energy through excitation and ionization of the target electron. Okay, so if I have a solid material here, okay, and a ray is falling on it, okay, when this ray will fall on the surface of this material, this ray will lose some energy, okay, this ray will lose some energy. And how will it lose the energy? By the excitation and ionization of target electrons, okay, of the target electrons, okay. So the projectile excitation and ionization is another method through which these rays will lose the energy, and electron capture and elastic collision with the target atom, and the electromagnetic radiation means Bremsstrahlung and Cherenkov effect, okay. So these are the different methods through which my incoming ray will lose energy on falling on the target metal, okay. So the next thing that we have is the widespread use. Is there widespread use? Means why are they used all over the world? So these are used all over the world because of the basic simplicity of its methodology. Okay, because they are simple. Their methodology is simple. They are low cost of its materials, and there is a great versatility of its possible application. And there is a small geometry of detectors, the ability in certain cases to reserve their track record, and the last thing is their rigidness. Okay, so these are some of the advantages, I can say. These are some of the reasons that the solid state nuclear detectors are used worldwide. Okay, so in this slide I am going to explain the basic principle of the working of solid state nuclear track detectors. So when a charged particle is incident on the surface of solid state nuclear track detector, so if I have a solid state nuclear track detector and a charged particle is incident on this surface, okay, they induce hidden tracks along the special orientation. So these charged particles will produce some hidden tracks on the surface of this material, okay, and the chemical etching fix these tracks and makes them visible. So as I've told you earlier, that the tracks that are formed by these radiations are so light, are so very small that they are not visible through a simple microscope. So what we do is just to perform a process of chemical etching on this sample. Okay, we perform a process of chemical etching on this sample, and the chemical etching will produce some deep tracks. Okay, it will make those tracks deep. Okay, so for example, if I had this track that was produced by the incoming radiation after chemical etching on this material, this track will go deep. Okay, and when this track will go deep, then this will be visible through the optical microscope. Okay, so an example is the CR39 track detector that will be explained in this video. Okay, so moving on towards the next slide, what I have here is the applications. Okay, so here in this slide I'm going to tell you the example of CR39 as a solid state nuclear track detector. So what is CR39? CR39 or allyl diglycol carbonate. Okay, CR39 is also known as allyl diglycol carbonate, is a plastic polymer commonly used in the manufacture of eyeglasses lens. So CR39 is actually allyl diglycol carbonate that is normally used in the manufacture of eyeglasses lenses, and the abbreviation CR39 means the Columbia resin 39. Okay, which was the 39th formula of a thermosetting plastic. Okay, so it is the 39th formula of the thermosetting plastic. Okay, so CR39 is a solid state nuclear track detector and extensively used in various experiments. Okay, so where it is used in the radiation detection, okay, like radon concentration measurement, okay, and it is used in space sciences for measurement of cosmic rays, for fission and fusion research in nuclear sciences, and for the identification of nature of nuclear particles. Okay, so these are the applications of the CR39 detector. So in this slide I'm going to explain the disadvantages. So the main drawback of using SNTDs is actually in radiation measurement is actually limited to counting the number of alpha particles. Okay, first of all, after performing the experiment, you need to count the number of alpha particles. Okay, the number of alpha particles that have etched their tracks on the surface of a sample. And the second thing is another drawback is the difficult to distinguish between the tracks of alpha particles of different energies. Okay, so it is not easy to distinguish between the different tracks that are formed by different alpha particles of different energies. Okay, so these two are the main drawbacks. These two are the main disadvantages for SNTDs. Okay, so the next thing that we have is advantages. So advantage is that it is a cheap process. So the second point is it is a passive detector, and passive detector means that it needs no power. Okay, we do not need an external electricity for this process or external power source for this process. So the third thing is the permanent record. Okay, so the sample on which our particles had etched their tracks, okay, the sample is a permanent record of our results. Okay, and the fourth thing is the integrated detector. An integrated detector gives the average value over the long time, 3 months. Okay, these 5 are the advantages for using the CR39 detector. Okay, so now I'm going to explain this process through an experiment. Okay, so for an experiment, what you need to do is to take a CR39 detector, and CR39 detector should be 1 by 1 centimeter of thickness. okay, should be 1 by 1 centimeter of thickness of 1 millimeter. Okay, this should be the area of the CR30 detector should be 1 centimeter by 1 centimeter, and the thickness should be of 1 millimeter. Okay, so 3 sets of sample were mounted on thick copper substrate to block the exposure from the back side. Okay, so what we did, we took a thick copper substrate. Okay, we took a thick copper substrate. Okay, then what we did, we just placed our three sets of the sample were mounted on thick copper substrate. Okay, so 3 sets of sample were mounted on it. 1, 2 and 3. Okay, so 3 samples were mounted on the surface of a thick copper substrate. Okay, this thick copper substrate was used because to stop the radiation exposure from the back side. Okay, to stop the radiation exposure from the back side. Okay, and the second thing what we did was, on the front side 2 sets of samples were covered with aluminium films. Okay, these 2 sets were covered with an aluminium film. Let's just say that aluminium film is green, so these 2 were covered with an aluminium film. Okay, here it is an aluminium film, and this was also covered with aluminium film. Okay, so this surface and this surface was covered with aluminium film. So this surface had an aluminium film of 15 mm. Okay, this surface had an aluminium film of 15 mm, and this surface had an aluminium film of thickness 10 mm. Okay, and our third sample was kept uncovered. Also the third sample was kept uncovered. Okay, so then what we did, we just exposed them to our radiation. So let's explain on next slide. The first film that had a 15 millimeter of thickness will block out the lower 2 particles. Okay, so what we have here is, we have particles of 3.86 mega electron volt energy, 2.7 mega electron volt energy. Okay, and 5.11 mega electron volt energy. So we have 3 particles. We have 3 alpha particles of 3.86 mega electron volt, 2.7 mega electron volt, and 5.11 mega electron volts. So we have 3 particles that we are going to throw onto these 3 samples that we have just prepared in the previous slide. Okay, so what happened? So this is my sample 1, this is my sample 2, this is my sample 3. This first sample has an aluminium film of thickness 15 millimeter. This second sample has aluminium film of thickness 10 millimeter, and the last sample is not covered with the aluminium film. So what we have here is, we have 3 different types of alpha particles. Okay, we have 3 different types of alpha particles. Okay, so first particle has an energy of 5.11 mega electron volt. Okay, the second particle has an energy of 3.86 mega electron volt, and the third particle has an energy of 2.7 mega electron volt. Okay, so we have these 3 types of particles. The first one has high energy, the second one has medium energy, and the third one has the lowest of energy. So as you can see here, the first film has a thickness of 15 millimeter. So when my alpha particles of 5.11 mega electron volt will fall on this film, they will pass through this film and will reach this sample. Okay, and will interact with this sample and etch some tracks on it. Okay, whereas the particles with low energy like 3.86 and 2.7 mega electron volt, these particles will not be able to cross the 15 millimeter thickness of the aluminium sheet. Okay, so these particles will be blocked. For 3.86 mega electron volt and 2.7 mega electron volt particles will be blocked by this aluminium sheet, whereas the 5.11 mega electron volt particle will pass through this aluminium sheet and will affect the CR39 detector and will etch some path on the surface of the CR39 detector here. Okay, so the second film had a thickness of 10 millimeter. Okay, so the second film has somewhat a less thickness as compared to the first sample. So in this case, what happens is that the electron of energy 5.11 mega electron volt and 3.86 mega electron volt will pass through this layer, will pass through the aluminium layer and will affect the sample. Okay, whereas the alpha particles of lowest energy, the alpha particles of 2.7 mega electron volt energy will not be able to cross this aluminium sheet. Okay, they will be blocked by the aluminium sheet. Only the particles of 5.11 mega electron volt and 3.86 686 mega electron volt will be able to cross this aluminum sheet and will affect the sample. Okay, and after affecting sample, what they will do, they will produce some tracks on it. Okay, and for uncovered detector, since my last sample is of uncovered detector, and uncovered detector does not contain any aluminum sheet, so what happens is that all of my three types of alpha particles, the 5.11 mega electron volt, 3.86 mega electron volt, 2.7 mega electron volt, all of these three types of the particle will interact with this surface. Okay, so this sample will contain the paths of all three types of particles, whereas this sample will contain paths of only two types of alpha particle, and this sample will contain paths of only one type of particle. Okay, so that was our experiment. So moving on, each sample was irradiated for 5 seconds. So all of these three samples were irradiated for 5 seconds with alpha particles using CF252 standard source of energies. Okay, so what we did, for generating the alpha particles, we used a source of CF252 to generate the alpha particles, and we irradiated our samples with the alpha particles for just 5 seconds. Okay. And as I have told you earlier that there were three types of alpha particle, the energy with 5.11, the energy of 3.86 and energy of 2.7 mega electron volt, which were produced by changing the distance between the detector and standard source. Okay, so these different energies, how they were produced? They were produced by changing the distance between the detector and the standard source. So the next thing that we have is the irradiation process was done in air, and a manual shutter was used to close the opening window between the source and the detector. Okay, so if this is my sample here, okay, let me just say that if this is my sample here and this is the source, okay, and this here and this here is the source from where the alpha particles were coming. So what I did, I just used a blocker, I just used a shutter to stop the alpha particles from reaching the detector. Okay, what I just used a manual shutter to stop the path of alpha particles. So if the shutter was closed, the alpha particles weren't able to reach my samples. Okay, so what happened is that I just opened the shutter for 5 seconds. I just opened the shutter for 5 seconds, and after 5 seconds I closed the shutter, and after closing the shutter, the alpha particles were not able to reach the detector. Okay, they were not able to reach our samples, our three samples. Okay, so that was the process. And moving on towards the chemical etching. So now what happens is that the radiation will form some tracks on the surface of the sample. Okay, we were having three samples. Okay, we were having three samples. Okay, as I have drawn earlier, we were having three samples, and on the surface of all these three samples there will be some hidden paths that will be induced, that will be produced by the incoming radiation of alpha particles. So what we need to do now, we just need to place each of these sample in 6.25 normal NaOH chemical solution at 70 degrees C for 6 hours. So why is this required? This is required to make the etching tracks visible. Okay, as I have told you earlier that the tracks that are formed on the surface of these sample due to the incoming radiation are hidden. Okay, these are so light that you cannot see them through a microscope. So what we need to do is we need to perform a chemical etching on all of these three samples, and we perform chemical etching by the process by placing the sample in a 6.25 normal NaOH chemical solution at 70 degrees C, and we heat it for, at 70 degrees C for 6 hours. Okay, after etching, the CR39 detector thoroughly washed with the distilled water and dried in the open air. So after the process of this 6 hours, what we do, we just wash it with distilled water and dry it in an open air. Okay, so the next thing we have is the etch pitch counting. So the number of tracks on the surface of all of the three samples were counted using the optical microscope. Okay, using the optical microscope, what we did, we just counted the number of tracks that were formed on the surface of each of the sample. Okay, so the next thing what we did is the calculation. Okay, so we have here the three micrographs that were taken through optical microscope. Okay, so the first micrograph here shows the tracks of the alpha particles that were at the energy of 5.11 mega electron volt. Okay, this was sample number 1. The sample number 1 was covered with the 15 millimeter aluminum film. Okay, and as I have told you earlier that the 15 millimeter aluminum film does not allow the passing through of the particles of 2.7 and 3.86 mega electron volt energy. Only those particles that had the energy of 5.11 mega electron volt were able to cross the 15 millimeter aluminum film to reach the CR39 detector. Okay, so this picture here shows the tracks, this and this here. These tracks are only of the particles of 5.11 megavolt energy. Okay, and this second sample, as you know about the second sample was covered with a 10 millimeter thickness film. Okay, and you know that the second sample allowed the passing of 5.11 and 3.86 mega electron volt energy. So this sample will contain the tracks of the particles of 5.11 and 3.86 mega electron volt energy. Okay, and the third thing here, the third was the sample that was not covered with any aluminum film. Okay, the third sample was uncovered. So here the third sample contains the tracks that were formed by 5.11, 3.86 and 2.7 mega electron volt energy. Okay, so as you can see here that the first diagram here shows a lesser number of tracks because only the particles of 5.11 mega electron volt were allowed to reach the CR39 detector, and second contains more number of tracks because in this the 5.11 mega electron volt and 3.86 mega electron volt. Okay, these two alpha particles were able to reach the CR39 detector. And the third here, the third sample, the picture of the third sample shows that there are a lot of tracks. So these lot of tracks are of 5.11 mega electron volt, 3.86 mega electron volt and 2.7 mega electron volt. Okay. So as you can see that the tracks on the first set of detectors that were covered with 15 millimeter aluminum are only due to the 5.11 mega electron volt. Okay, so these are only due to the 5.11 mega electron volt, and the second set, the tracks are due to the 5.11 mega electron volt and 3.86 mega electron volt alpha particle. Okay, so the difference between the first two diagrams is only due to the addition of the 3.86 mega electron volt in the second. Okay. So what I have here is the detector number 1. Okay, so detector, the sample number 1, what I had on sample number 1 was 15 millimeter sheet. So the average number of tracks on that should be right 8.80 plus minus 1.30. Okay, and similarly on detector number 2 with 10 millimeter aluminum sheet should have the average number of tracks around about 16.85 and with an average of 2.75 plus minus. And the third detector that was uncovered should have to 21.83 with plus minus 3.81 number of tracks. Okay, so the next thing that I have, the table here. Okay, so this table here shows the average number of tracks for 15 fields of view take for each detector. Okay, so there is a slightly difference between the expected number of tracks and the experimental value. So as you can see here that we should have a difference of plus minus 1.30. so this difference is due to the error in the irradiation. Okay, so this difference is due to the error in the irradiation time, because as I've told you earlier that as this was my sample and this was the source from where the alpha particles were coming. Okay, so this was the source from which the alpha particles were coming. So what we used a manual shutter here. Okay, so we used a manual shutter here to block the path of the alpha particles after the 5 seconds. Okay, so the difference in the number of tracks is only due to because a manual shutter was used to close the opening window between the detector and standard source, so there can be a manual error here. Okay, so due to the manual error the results, the number of tracks can change. Okay, so this is our diagram for the process. Okay, so as you can see here that I have a CR39 detector, irradiation of CR39 detector film. Okay, so as you can see here, let me just zoom it a bit. Okay, so as you can see here that I have a CR39 detector here, and here I have the irradiation of CR39 film. So what I did, just irradiated, this is the source, this is the CR39 film. I just irradiated the source, I just irradiated the CR39 film with the source of alpha particle. So what happens, particles now contains tracks. Okay, so what I did, I just etched, I used the process of chemical etching with the 6 normal KOH at 72 degrees C for 90 minutes. Okay, so in this process I have just changed the solution. Okay, in the process that I have just told you earlier, I used the NaOH solution. So here I am using the KOH solution. In this diagram I am using the KOH solution for the chemical etching. Okay, so after chemical etching we take a photograph. Okay, we take the photograph by using our microscope, and then we analyze this image. We analyze our photograph through the computer. Okay, so the next thing what we have here is the conclusion. So this slide is our last slide. In this slide I'm going to explain all of the conclusion of my whole lecture of whole SSNTDs. So the aluminium fiber was used as an energy window for alpha particle measurement with SSNTDs. The aluminum filter was used to stop the path of alpha particles, and the second is the counting and calculation process of tracks was developed effectively, used to discriminate between the alpha particles at different energies. So what we did, we just counted the number of tracks on the first sample, the second sample, and the third sample. We calculated and just we subtracted, and by subtraction we can get the number of tracks that were formed. So just by subtracting we can get the number of tracks that were formed by 5.11 mega electron volt alpha particle, by 3.86 mega electron volt alpha particle, and 2.7 mega electron volt alpha particle. Okay, so the resolution of the method is high and does not need calibration of track diameter versus alpha energy. So the resolution of this method is very high. Okay, and the last thing that we have is here, it may provide researcher and radiation protection officer with a cheap and powerful tool for measurement of alpha radiation. Okay, so that was all for today's video. Thank you and Allah Hafiz. Don't forget to like the video and subscribe the channel. Okay, so if you have any question you can ask in comments. I will surely answer. Allah Hafiz.